example of application of this invariant that I introduced, and in particular I showed that the simplest case for this invariant which is like this. I recall that we consider projective varieties of codimension C, and our invariants we start with variety Y, then we consider its second, we run as embedding, and we consider the following invariants. First of all, K2, and this is the first secant variety, which is equal to the ambient space of X. Then we have the number of quadratic equations, E2 of Y, where this is the ideal sheaf. And then we have secant deficiencies. And these secant deficiencies of X are several first of them up to L2 are equal to 0. And then they start monotonously increasing. Up to the nth, n capital. And we found, for example, that in the extremal case, when L2 is equal to C, and I proved that it's always at least C, then this is equivalent to E2 equal to this number. And this is the maximal possible value, so that for any Y, the number of quadratic equations doesn't exceed this number. And equality holds if and only if L2 is equal to C, or equivalently delta C plus I is equal to I, K2 is equal to N, and equivalently, the degree of Y is minimal possible. And the minimal possible value is this. So this only one equality is equivalent to a series of such interesting consequences. And next I'll, this is the maximal number of equations, and then I will see what happens if the number of quadratic equations is big but not maximal. But maybe before doing that, I'll show you that the very simple results that I proved without any effort allow us to compute many invariants. Some of them classical invariants, some of them I mentioned before. So let's return to the functional Waring problem, which I mentioned. So, and it's a classical problem which asks a solution to the answer to the following question. Suppose we have, to keep our notation, y, x is equal to vd of p1, and we're interested in the order of this variety or the number k. So we, as usual, we have this chain of inclusions. Okay, 0 of x, which is equal to the ambient space. And this number k0 plus 1 is called the order of variety x, And because when we consider Segre variety, this coincides with the usual notion of order of matrix. And the question put in simple words is the following. Take a general form of degree d in these variables, and there are two possible questions, when f is general and when f is arbitrary. So we consider the general question, which is easier. And we ask how many linear forms are required to represent a general linear form as a sum of their d's powers. So we want to represent it in the following form. Where L is linear form, and K is minimal. And this question is analogous to the classical arithmetical Waring problem, which asks how many powers are required to represent an arbitrary natural number as a sum of powers of this order. For example, every natural number can be represented as a sum of 4 squares, and so on. And here we would like to find out what is this minimal number. And of course, you see immediately that this question is equivalent to finding the order of this variety. And therefore, this is similar to this number k here, but for second variant as embedding. And this question has been studied for maybe 1.5 centuries. And for general form, there is now a complete answer to this question, although the proofs are not yet completely satisfactory, but from the point of view of aesthetics, they are correct. And for arbitrary form, if you consider here f to be an arbitrary form, the answer is still unknown. Because for some forms, some closed subvariety of forms, you may need more d's powers than for a general form. And also, I mentioned that this, using Terracini lemma, this equation can be formulated differently. This same number k, or k plus 1, because we start with 0, equivalently you can ask.
So the variable of the fd is from x0 to xn?
Yes, yes, because we consider equivalently find maximal k such that for a general collection of points in this Pn, there exists a form or a hypersurface, maybe a hypersurface of degree d singular at these points. So it's clear that for one point there is always exists a hypersurface singular at this point, for 2 points also, but how many each point imposes an additional condition on our form, and when can we find a form with many singularities, a hypersurface with many singularities? And these questions, as I explained, are equivalent to each other because of the Terracini lemma, which says that to compute the dimension of secant variety, it suffices to compute the dimension of the linear space spanned by their tangent spaces. And a hyperplane under the Veronese embedding, hyperplanes correspond to hypersurfaces. Singular, saying that a hypersurface is singular at some point means that a hyperplane is tangent to this Veronese variety at this point, and therefore we should find hyperplanes that are tangent at many points. And this is such hyperplanes are tangent to the secant variety. So when the secant variety is non-trivial, high secant variety, then that means that we can find such a form. And so I'll write the answer to this problem. I will not prove it, it requires a course of lectures at least of this length, but I'll write the list of exceptions, and then I'll comment on this list. So the first and the only series is as follows: d equal to 2. So we consider the variety which we studied in detail, and now, what is this question actually? We ask to compute, but we have some guess. And this guess is classical because we know that we should compute the dimensions of these secant varieties. But we have a guess. The maximal possible value for this, as we several times computed already, is the following. It's for example, for k equal to 0, we get n the dimension of x. For k equal to 1, we get 2n plus 1, and so on. So these are the maximal possible dimensions of secant varieties. And usually we expect that they should be like that. And then to compute this number, we should find out when the following equality takes place. We know that we know the dimension of the ambient space for this Veronese, and we should find the smallest k0 with this property, and this will be the expected value. And the cases when the real value, the actual value, is larger than expected, because if the dimensions are smaller, sk are smaller, then we'll get a longer chain of secant varieties, not trivial secant varieties. And so so I'm giving a list of exceptions to the case when they are expected, when these numbers are expected. So in this case, for example, expected order, I'll write a table. Expected order, actual order, and maybe some comments. So in this case, the question is how many squares of linear forms are needed to represent a general quadratic form. And the expected order is this. It's computed by this formula, so we know that here d is equal to 2, and we compute this and we obtain this value. And the actual order is n, and this you know very well because any quadratic form can be represented as a sum of n squared, maybe n plus 1. But yes, here k, not order, but k0, which is 1 less. So. And so this is an exceptional series which is everybody knows. But except for this, there are very few exceptions, and 3 of them are related to the case d equal to 4. And the first case, very famous case, is V4 of P2. And here it's in P14. Here the expected order is 5 and the actual order is 6. And so maybe I'll tell you in more detail about this example, which is very famous. So this was a classical problem. In a classical language, it concerns representing ternary quartics. Ternary quartics. Ternary means of 3 variables, and here P2 means that they are in 3 variables, and quartic means that the degree is 4. And this was a famous problem, very popular 150 years ago, and it's expected that each ternary quartic can be represented as a sum of 5 by squares, they call it, 5 false powers. But Klopsch has solved this problem and proved that this is not so. That actually the ternary quartics representable in such a form, they form a hypersurface in the space of all quartics. The degree of this hypersurface is 6. I'll explain this with our methods immediately. And then after that, Luros gave an interpretation of this special quartics, which are now called Luros quartics. Now let's regard this problem from our point of view, in particular from the point of view of this theorem. So instead of studying V4 of P2, we can study V2 of P2. So we put, as we did previously, but for arbitrary, this Veronese variety we denote by Z, and now we put, and this will be our Y in the formal notation. And X is then V2 of Y, as usual. And we would like to compute K2 of Y. And we know everything about this. First of all, we have general theorem that K2 always satisfies this inequality for any Y. You remember this theorem, a very easy theorem, and it immediately has implications here, because what is n here? N here is 5, because the Veronese surface lies in P5. And furthermore, Veronese surface is a variety of minimal degree. What is the degree of Veronese surface? In our case, the degree of Veronese surface is 4. And therefore, it lies in P5, and it's equal to C codimension, which is equal to 3, C plus 1, and this is a variety of minimal degree. And therefore, we know all the invariants in this case. And this means in particular that K2 is equal to n, which is equal to 5. And this means that 6 and not 5 quartics, false powers, are necessary to represent arbitrary form of degree 4. But we know more than that, because we know that in this case as you know, we have the maximal number of quadratic equations. You see, it's equal to C E2 is equal to C times C plus 1 over 2, and in our case it's equal to 6 because C is 3. And we know that we have this equality, where that means that the secant variety is obtained from the secant variety of the Veronese. Sorry, here Z is a different Z. It's Veronese of the ambient space, which is P5. So the same Z, but for different dimensions. And we know what is this, because Z5 of Z is already the ambient space, P14. And the preceding is a hypersurface, because what is this variety? C4, S4, the fourth secant variety of the Veronese. It's defined by vanishing of determinant. So we have here 6 by 6 matrices, because symmetric matrices. And we have the determinant is a degree 6. Hypersurface. And this equality says that in this space, S5, in the ambient space P14, the quartic that can be represented as a sum of 6 squares form a hypersurface of degree 6. Just the intersection of our determinantal hypersurface with this subspace defined by 6 equations in the ambient space, corresponding to quadratic equations of the Veronese. And so we understand everything in this case, and we see why we have an exception. So maybe to finish with this, I give you the remaining exceptions, and almost all of them are similar. So, and can be explained in a similar way. So the second exception is D equal to 4, and a similar variety here in P34. Third exception is D equal to 4 and P4. Here expected number is 9 and the actual number is 10. Here expected number is 14 and actual value is 15. And one final exception, which corresponds to D equal to 3, and you get V3 of P4. So this is symmetric to V4 of P3 here, also in P34, and this is different. So all these cases, this is an exercise, cases 2 and 3 are dealt with in a similar way, and only cubics should require special attention. So you see that without any effort, by applying some general theorems, and namely this theorem, this inequality, which we proved very easily, we get most of the exceptions of this functional Waring problem, and with an explanation. We see immediately that not in all these cases, without any computations, we see that the corresponding forms which cannot be represented which can be represented in the expected number of sums of powers, they form a hypersurface. We know the degree of this hypersurface, and we know that this hypersurface is the restriction of determinant to certain linear subspace. So we get a very nice geometric picture of this functional worrying problem. Now, as promised, I'll come to explaining what to do with varieties who have many equations but not the maximal number. So I recall that the maximal number is computed in terms of codimension. And it's written here. So you always have this inequality for any variety. You have this inequality. So modulo 1 lemma, which I'll prove today, last time I explained you that the varieties for which this is equality are varieties of minimal degree. And now it's reasonable to compute the difference. So suppose we consider this number, epsilon 2 of y, as the difference between the maximal number of quadratic equations and the actual number of quadratic equations. And we are interested in the cases when this number is small. And it turns out that we can prove some theorem which allows us to bound the degree if this number of variety when this number is small. But to do this we need an additional property which I'll briefly recall. It's very easy. Suppose that y has, we take a general hyperplane section of y. And we would like to compare these numbers, E2 of y and E2 of y prime. And I already gave you an example showing that the right-hand term can be larger than the left-hand term. An easy example, you can, well, to give you an example, I don't remember if I gave it. So consider a quadric in P3, quadric surface, and take a curve on this quadric of type 3, 1. So it's equivalent. There are two lines, one family and the other family, and take a curve which has this form. This is a rational normal quartic. Not normal, sorry. It's a rational curve of degree 4. Clearly? And actually, this curve is not linearly normal. It's a projection of a curve C tilde in P4. C tilde in P4 is just a rational normal curve, the Veronese image of projective line, and it can be projected so that it's contained in one quadric. So E2 of C is equal to 1. Why? Because we know that this is a quadric, therefore this gives us one equation, and there cannot be another quadric because the intersection of two quadrics has degree 4. And therefore, if it contains this curve, it should contain another line in this family. So it's impossible. So this curve has only one quadratic equations. But now take a hyperplane section. Intersect this curve with a plane. In the plane, you get 4 points. So because the degree is 4, so you get 4 points in the plane. Of course, this quadric intersected with the plane gives you one conic, but there is another conic because any 4 points in general position in plane, they are contained in one dimension in a pencil of conics, because you can draw a conic through any 5 points in general position. So E2 of C prime is equal to E2. And now it's you can always show that you have this inequality because of the exact sequence like this. Then you restrict these quadratic equations onto the hyperplane. And the dimension of this is E2 of y. Here the dimension is 2 of y prime. But when you go on with this exact sequence, you get H1 of this sheaf. Here you have an inclusion because y is non-degenerate, is not contained in a hyperplane. And here this space, as you know probably, it measures the failure of y to be linearly normal. So if y is linearly normal, if y is not a projection, then this is 0. And then E2 here is equal to E2 here. But if, as in our example here, the variety y fails to be linearly normal, like this curve, then this term is non-zero, and therefore E2 is larger. And this will be important for us because we'll actually measure the number of equations of the variety obtained by intersecting y with a general PC. So if we have a variety y, we can intersect it with a linear space, general linear space of complementary dimension, and then we get finitely many points. And we know that E2 for this collection of points satisfies this inequality. And this we'll be able to bound very easily. And to do this, and also to complete the proof of the theorem that I proved yesterday for characterization of varieties of minimal degree, I need to prove a proposition, which I formulated last time. And it's quite a general proposition, which is often useful. So it concerns a collection of points. Suppose we have a finite collection of points in PR that span PR. So we assume that the linear span is PR. And also we assume that any subcollection of degree of t plus one of them is in general position. You take any subcollection and being in general position means that this is the span linear space of maximal possible dimension, here t. So for any collection of points, we define this number t as the number for which any t plus 1 points are in general position, but there exist t plus 2 points for which they are not in general position. For example, if you have 3 points in a line, then t is equal to 1. If you have do not have 3 points on a line, do not have trisecond lines, that means that t is equal at least 2, and so on. So for any collection, you can define two numbers, r and t. R is the dimension of the linear space they span, and t is the number such as any subcollection is in general position. And the theorem says if k is at most r plus t, then the images, as usual, I denote the images by xi. Then these points are in general position. So what is the idea? The idea is that if we have some collection of points, then applying the Veronese map makes them more independent, more linearly independent, so the images xi span a linear space of larger dimension. And this gives us a control of this fact. So before proving this, if I have time, I formulate some corollaries, and which will show how this can be applied. This is quite a general theorem. So corollaries will need some cases. The first case is suppose we have a finite collection of points such that they span they span a linear space of dimension. You expect dimension k, but we suppose that they span a linear space of dimension at least k minus 1, which is 1 less than maximal. Then the Veronese images already span something of maximal dimension. So even if the dimension of the linear span of y's drops by 1,
k minus 1 would be bigger into k minus 1, right?
for here k minus 1 and here k. Okay. So here it needn't be maximal. For example, you may have just a simplest example. Suppose k is equal to 2. You have 3 points on a line. Here you have this equality. They span a line. But if you consider the Veronese images, these images are not contained in a line. So they span something of dimension 2.
In the proposition, for any k plus 1 point are generally in position, then that is for any, right?
No, we just have a finite collection of points. This proposition deals with finite collections of points.
Yes, but you have to choose y, I0, ik.
No, it, it's any subcollection.
Yeah.
That any subcollection of t plus 1 points span linear space of maximal dimension.
Yes.
This is the definition of t.
Yes.
And t is the minimal number with this property.
Yes.
And then we show that for k not exceeding this, the images are in general position. They span maximal possible linear space. So this is the first application, and this is this application that we used last time to show that if a variety has maximal number, this number of quadratic equations, then it's variety of minimal degree. Now we'll also use another corollary. Suppose in the above notation, suppose that k, in the notation of the proposition, doesn't exceed 2t. Then these points are in general position. And this is immediate consequence because we can throw out some points. If there are more points than 2t, we can throw out them, and this condition will be satisfied. Because in principle, we here, in the proposition, we can put here not 2t, but a plus t. But clearly, t doesn't exceed r, because r is the dimension of the linear span, and t is the dimension of subspace that's spanned by t plus 1 points. So this is also an immediate consequence. And the third one, which I really need, it's an immediate consequence of 2. Let's consider a variety as above, and we take the intersection of y with a general linear subspace of dimension c, codimension. So here you get a finite collection of points, and take these points here in this intersection. And last time I showed that these points are in general positions, that any c plus 1 points span this ambient space. This was shown last time. It's widely known that if you take general hyperplane section of a curve, then the points are in general position. Then the points x0, yes, and suppose that k is at most 2 times the codimension. Then the points x0, xk are in general position. Here you have k. In particular, suppose that the degree of c doesn't exceed 2 times the codimension plus 1. Then we can take the Veronese image of this intersection, and this is in general position, is a collection of points in general position. And this immediately follows from this, because when, suppose for example that we have this inequality, this means that t is equal to c. Because as I told you, if you have any variety and intersect it with a linear space whose dimension is equal to the codimension, and they meet in infinitely many points, then these points are in general position. So here t is equal to c, and you can apply 2 to get this. Now I wonder, should I prove this proposition or not? Because if I prove it, the proof is very easy using secant varieties, but then I will not have time for applications. Maybe I start with writing out some applications, and then we'll see if I have time for the proof. But an immediate application of this corollary 3 of this proposition allows us to prove the following.
In this number 3, you should assume k less than equal to 2 times c? What is
C here?
Yeah,
Yes, 2 times c. And we still have 0, so actually it's 2 times c plus 1, because we start with 0 and not with 1. And c is the codimension.
If the number is bigger, then we cannot guarantee that?
We can, no, if the number is bigger, we should choose that many points and not more, because otherwise we cannot apply 2. We know only that t is equal to c, and we cannot apply the proposition because this gives a limitation for this method. However, if the codimension is not very small, this is not so bad. So a consequence of this is the following proposition. So we keep the same notation. We take a complementary linear space, and we have the following. Suppose that what does it mean? I recall that epsilon 2 is the deficiency, is the difference between the maximal number of quadratic equation, which is equal to this, and the actual number of quadratic equations. So it's always positive, and if epsilon is small, that means that we have many quadratic equations. Not the maximal number, but many. And so we can show that this is equal to this. Suppose that the difference is less than codimension. For example, 0 is good, 1 is good, up to codimension. And then we have the following bound for the degree. Is equal to C plus 1 plus epsilon 2 of this intersection. And we know the inequality, which I proved. That the number for linear section, the number of quadratic equation becomes larger, may become larger, but not smaller. So we always have, if there are many quadratic equations, then the degree is small. So if, for example, the ultimate case is when epsilon is equal to 0, then we have a variety of minimal degrees that we proved last time. But if not, we still can get a bound as long as epsilon doesn't exceed codimension. So we can say something about the varieties, not only of minimal degree, but of those varieties whose degree is different from that of minimal degree, at most by the codimension. And part B is in the opposite direction. Suppose that you know that the degree doesn't exceed 2 times the codimension plus 1. Then we can say something about the number of quadratic equations, but not too much, but still rather much. We can say we get information about the quadratic equations of its linear section. So this means that we can compute the number of we can exactly compute the number of quadratic equations for its linear sections. But if this sum of these linear sections are not linearly normal, then we may have more quadratic equations than here. And this is an almost immediate application of this number 3 here. So let me explain once more. If we knew that all linear sections of y are linearly normal, then we get equality here and equality here. So we know exactly what is the degree of variety with many quadratic equations, as soon as the number of quadratic equations satisfies this restriction that it's maximal. It differs from the maximal one by at most codimension. And some special difficulties, which are, well, I could illustrate them by example, is when some linear sections fail to be linear normal. Then still this linear section may have a lot of quadratic equations, but our original variety may have fewer quadratic equations. I show it by example. But still we know that if there are many quadratic equations, then the degree is small. Here is the bound. So, for example, let me give an application of this.
Let me ask a question.
Yeah.
Echelon 2 the linear section is always smaller than the
What do you mean 2?
E2. Echelon
E2, yes.
is always less than echelon y. Is that always true?
What? Yes, this is always true. Both A and B are always true. What is the question?
Echelon 2 linear section is less than or equal to echelon 2y.
So you refer to which line? This line?
Next.
Well, that makes
Here.
it equals A, but E2 is
This is not E, this is epsilon.
getting bigger.
Is it bigger?
Yeah.
Yes, when you take linear section, as I showed by example, E2 may increase. For example, and this is always connected with the failure of some linear sections to be linearly normal. But the degree, the first line, can always be bounded because the degree does not depend on taking linear sections. In the other direction, there are some additional restrictions that if you want to get many quadratic equations, you always get it for linear sections, but not always for the variety itself, because some of its linear sections may fail to be linear normal. So as an application, consider the case, we considered the case of varieties of minimal degree. Let's consider the case of next to minimal degree, del pezzo varieties. So these are defined by the following. Suppose that your variety y has degree c plus 2. It's one more than the minimal degree. One more. And suppose that y is not, to ensure that its linear sections are not are linearly normal, it suffices to assume that y is not a birational projection of something. For example, smooth. Of some variety of minimal degree. Because when it's a projection of variety of minimal degree already. For example, all this is true when y is smooth. Then this is equivalent to L2 equal, this is A and B, and they are equivalent. This is equivalent to the following: L2 of y equal to c plus 1, and this is one more than the minimal value, as I recall. And then we know a lot. We know that we can write out delta. The first c plus 1 are 0, and then starting with the next one, we get this inequality, this equality. And K2 is equal to n, again the minimal possible value. and E2, as I already mentioned, drops by 1. And there is a classification of this variety. There are two series which exist in all dimensions. This is a cubic hypersurface and the intersection of two quadrics. But besides them, there is complete classification by Fujita. Maybe the most interesting example is Grassmannian of lines in P4, but there are some other interesting examples. What prevents you from proceeding further, where here epsilon is equal to 1, then to consider epsilon equal to 2 and 3, and so on. Actually nothing prevents, but you should always, the only problem is to control when the linear sections are linear normal or not, and I think that this can be done. Well, my time is coming to an end, so I do not have, cannot go into details, but maybe I should say that, so here I introduce some new invariants, and to show to what extent they are useful, you need to experiment with many examples. I actually did not. I gave you two series of examples. Maybe I checked what happens for surfaces in P4. So let S be a surface in P4. What are the possibilities for this invariance? Maybe I write all the possibilities, and you'll see that although these invariants do not give too much information, particularly in this case where the codimension is small and few possibilities, of course, here the information is very limited, but still they allow to distinguish between several cases. So what are these cases? First case, E2 is equal to 3, and then this implies that L2 is equal to 2, and this is a variety of minimal degree, and you get the following invariance. Here, that's a special example. That's a cubic surface in P4, which is a blow-up of projective space. This is the only variety of minimal degree. Second example, E2 is equal to 2, and in this case, X is a complete intersection of two quadrics. L2 is equal to 2, because this is also a variety of minimal degree. E2 is equal to 2, L2 is equal to 3. Delta 4 is equal to 2, K2 is again equal to 4. So third case, E2 is equal to 1. Here L2 is also equal to 3, but delta 4 is not 2 but 1. And K2 is again equal to 4. And the case 4, E2 is equal to 0. There are no quadratic equations. And there are two subcases. For A is L2 equal to 4. The deltas are equal to 0, and K2 is equal to 4. And for B, L2 is equal to 3, delta 4 is equal to 1, and K2 is equal to 4. So not so many cases, but I should explain that first we obtain a complete classification by the number of quadratic equations. This is contained. Here for A is a general case, but for B is interesting. One can show that in this case your variety is necessarily projected Veronese surface, which has many very special properties. So at least even this first non-trivial example shows that these invariants allow you to distinguish between varieties having not only different number of quadratic equations, but also different properties of linear normality of this variety, or maybe its linear sections, and so on. So for this, this invariants serve well. In general, there are not enough examples to tell, but anyhow, to study the quadratic equations, I think that they are very convenient, as well as to study failure to be linear normal. For further study, you need more experimental data. So, unfortunately, my time is over, so I can only answer your questions.
For B is general case?
For
B is general or
no,
A is general?
for A is general.
For A is general.
Yes. So for A is general, and here, but you see here it's maximal possible value. This is because codimension is small. L2, that means that all deltas are equal to 0. But in general, it's usually not the case. Here you have little freedom. So, for example, I showed you that if the codimension is smaller than here it's half, the dimension is half, is equal to codimension. If the dimension is larger than codimension, then all delta cannot be 0, they showed in one of the lectures, and then you get some more interesting invariants. This is the only case when all invariants vanish, all deltas vanish. In all other cases, some delta is not equal to 0.